Okay, so now we're going to go and start to tackle the issue of stability of orbits and then eventually get into scattering. Um, Before we do that, though, I want to introduce the idea of effective potential. Okay, so let's go back to where we started. Kinetic plus potential equals total mechanical energy, which is a constant. Now, working in spherical coordinates here, 1/2 m, this will be r dot squared plus r squared theta dot squared. And really, we can say this is polar because we're working in a plane for an orbit, plus v of r equals e. Now, remember our reduced angular momentum. That's the angular momentum over the mass. L, that equals r squared theta dot. So I rewrite theta dot as being L over r squared. So our theta dot squared is L squared over r to the 4. If I go and stick that in to there, I get 1/2 m r dot squared plus L squared over r squared plus our v of r equals e. Okay, let's distribute the 1/2 and the m through. So we'll have m over 2 r, or here we'll write it this way, mr dot squared over 2 plus ml squared over 2r squared plus v of r equals e. Okay, now let's look specifically at this term right here. L is a constant by conservation of angular momentum since it's a central force. R, but notice here that this does not depend on r dot, and it doesn't depend on theta at all. If I just wrote this term down, you would assume that it was some sort of a potential. It's really part of the kinetic energy, but it only depends on the position. So this bit here usually gets the name centrifugal potential. So we can interpret this as the potential associated with just the centrifugal force part, if you will, of what's going on. All right. And if we look at the whole of this, both of these terms depend just on r. So we often rewrite this as u of r and call that the effective potential. So, I mean, if you like, you can say it's a potential energy due to the physical force and the centrifugal force, if that makes you feel any better. But, like I said, this is part of the kinetic energy, but as a part of the kinetic energy, it only depends on r. So when we're analyzing it, it's easier, because now this, if I rewrite it with this u notation, I now have an mr dot squared over 2 plus u of r equals e. And I look at that, and this looks like 1D motion. So if we follow this further, our r dot squared has to be greater than or equal to 0. So the only allowed values of our r are r such that the effective potential is less than the total mechanical, or equal to the total mechanical energy. So we can go ahead and put this all in. So if I go and look at, we'll plot, so that's R. This much right here is my ML squared over 2R squared. My V of R is going to look probably something like this. And so my U of R will be the sum of the two, probably ultimately looking something like that. All right, so then we can look at different possible energies. So if this were one-dimensional motion, we would say at best we approach, we turn around, and we go back out. So that's in one dimension. But our theta is continuously increasing because of the conservation of angular momentum. So this turns out to correspond to our hyperbolic orbit. If we were right on the axis, that would be a parabolic orbit. And if we're below the axis, so E less than 0, well, that is our elliptical orbit. With the special case that if this is our energy, that would correspond to a circular orbit. So here, for the hyperbolic orbit this, and for the elliptical orbit that, both of those would correspond to perigee. And then for our elliptical orbit, that would correspond to apogee. So we can say that we're executing some sort of harmonic oscillation. I mean, obviously the potential looks a little hanky. It's not just a clean, simple harmonic oscillator, but we're undergoing some sort of harmonic oscillation between apogee and perigee, if we view this as a purely one-dimensional thing, while allowing our theta to progress with time as the conservation of angular momentum demands. So this allows us to look at what happens if our orbit gets perturbed a little bit, and this gets us into the realm of nearly circular orbits. So we'll go back to our radial equation there, m over 2 r dot squared plus u of r equals E. Now what I'm going to do is differentiate this with respect to time. So bring down 2, cancel a 2, great. I get mr dot, differentiate what's inside r double dot. Differentiating my effective potential, that'll be a ddt of ml squared over 2r squared plus my v of r. And differentiating E will just give me 0. All right, let's work on these derivatives some more. So mr dot r double dot plus, okay, so I'm going to pick out an ml squared. And that should be, it was a little hasty to even say plus. I'm going to get an ml squared. When I differentiate this, I'm going to bring down a negative 2, cancels the half, and gives me a minus sign out front, leaving me with an r cubed in the basement. And then I have to differentiate r with respect to time, so I'm left with an r dot. And then similarly, I differentiate this. The trick here is I'm going to go ahead and use the chain rule on this guy. And so this is going to become dv dr dr dt. So dv dr, though, will be, since we're working in effectively one dimension, that'll be minus my F of r, since it's a central force, times r dot. That equals 0. All right, I can just divide everything through by an r dot and make it go away. So if I rearrange just a tiny little bit, I get mr double dot equals ml squared over r cubed plus f of r. Okay, so now let's consider the case where our orbit isn't that much different than a circle. So let's say the circle is of radius a. My will be an elliptical. My perturbed orbit, my slightly elliptical one, will be r equals x plus a. So we can differentiate that r, and that will give me r double dot will just become mx double dot plus ml squared over x plus a cubed plus f of x plus a. Now, what we can do is we can go ahead and expand this about a. Sorry, not plus, equals. So this will give me mx double dot equals. We'll look at the ml squared part. Oh, we can make it look better than that. So expanding here, expanding about a is effectively expanding about x equals 0. So I'm just taking a Taylor expansion. So I'll get an a to the negative 3, and then I have to differentiate that. So it'll be plus negative 3 times a to the negative 4x plus, following this further, I'll get negative 3 negative 4 over 2 factorial a to the negative 5x squared plus and such from that term. Then from the other term, I will get f evaluated at a plus x times the f prime evaluated at a, so df dx is what that means. Evaluated a plus x squared over 2 factorial f double prime at a plus and such. All right, now for a stable circular orbit, in that case, my x is just 0, and mx double dot will just plain become 0. Okay, so then putting into here, we're going to get that this equals ml squared over a cubed. And then all higher order terms drop because x is 0, plus f at a, and then all higher order terms drop because x is 0. So this tells us that ml squared over a cubed is equal to minus f of a. So now going back to our expansion here, where I had this minus a cubed a to the negative 3, this ml squared a to the negative 3, I can put in that that's minus f at a. So now I have, so returning to our regular orbit, so now we have mx double dot, which we can't make 0 anymore, will equal minus f of a for our first term. So then the next term we need to keep will be a 3 over a f of a x. And again, that's substituting in here, just pulling on a cubed and putting in f of a, well, ml squared a cubed and putting over a cubed and putting in f of a. Minus 6 over, whoa, minus 6 over a squared f of a times x squared plus and such. Plus, from the f part, I'll have an f of a plus x f prime evaluated at a plus x squared over 2 factorial f double prime evaluated a plus and such. All right. So it was good we kept a few more terms than normal because those cancel. All right, so we'll now group powers of x. So we'll have mx double dot equals 3 over a f of a plus f prime evaluated a x plus actually, I'm going to rewrite this all as something equals 0. Bear with me. So we're going to say plus, and then this will be a minus there, and a minus there. And then this will be plus 6 over a squared f of a minus 1/2 f double prime a x squared plus and such equals 0, which is where we're going with this. So if we want to look at our stability, let's call this term here term 1, and we'll call that term there, just the thing in the brackets, term 2. As we follow the expansion, the first thing we got to do is just get to a non-vanishing term in the brackets. So if the first term is if the first term itself is non-vanishing, we need this term to evaluate to be positive. If we do, then these terms will all be negative, the higher order terms. This will look like a harmonic oscillator, and we'll have a stable orbit. If this evaluates to be negative, then we just fly off. Here, if we get an x squared, we're just plain going to fly off if this is anything other than 0, thinking back to our treatment of the harmonic oscillator. So for even-powered terms, that's what will happen there. So we can go ahead and take a look. The general case we could have is there's our nice stable circular orbit, and then if we have a stable orbit, it could be something even as hanky as that, say, some sort of stable orbit that's oscillating about our circular orbit. All right, well, this is as far as we can take it with just the assumption that it's a central force. So now we need to assume that it's at least obeying some sort of a power law. And let's make it attractive, because obviously if it's repulsive, just looking at this first term, the sucker's going to fly off. All right, so we'll assume a force law that looks like f of r equals minus to make it attractive. We pull out some constant, r to the n. All right, so let's look at term 1, because the magic thing is term 1 positive? So we evaluate it for this force law. So we'll have a minus 3 over a, and then the force law itself will be minus c a to the n. That's good. And then for this bit here, we need to differentiate that. So we're going to get a minus, and then the force law itself needs to be differentiated. So we get a minus c, then we have an n, a to the n minus 1. And we demand that that be strictly greater than 0. to have stability. All right, so it turns out we can cancel all but 1 power of a there, and we can just cancel our c's. And we can cancel our other a right there, and we get minus and minus is so 3 plus n is greater than 0, or n is greater than negative 3. So our orbit is stable. So what we've got right now is if n is greater than negative 3, we have stability. And if it's strictly less than negative 3, it's unstable. But that leaves the issue of about n equals 3 itself. We can't just throw it arbitrarily into one of these two camps, because the thing is that it makes term 1 be 0. So then we actually have to look at term 2. And then keep in mind term 2, because it's in front of an even exponent, so if it's an even numbered term there. If it's non-zero, we're just going to fly off, because it's not a restoring force. And so possibly, so maybe it ends there. If it doesn't, maybe we'll have to go and take a look at term 3 and so forth. So this is tedious, but I think it's instructive. So let's just go ahead and we'll start looking at term 2. And at this point, we can just write our f of r directly as minus cr to the negative 3, because we've already treated all other possible cases. So our term 2, the thing inside the brackets, that's going to evaluate to 6 over a squared times negative c a to the negative 3 minus 1/2 times negative 12 c a to the negative 5. And if we go and take a look at that, so minus and minus becomes a plus, that becomes a 6, and we work that through. This is a to the negative 5, so hey, this is minus 6c a to the negative 5, this is plus 6c a to the negative 5, that's 0. All right then. So unfortunately, from a computational perspective, we can't yet say whether it's stable or not. If there was anything other than 0, we could have definitely said it's unstable, because we would have not a restoring force. So this means we need to go and look at some higher order terms. So we can take the expansion along a little further. So let's go ahead and expand. Oops, sorry. Let's go ahead and expand our previous result just a little further, since that's where we seem to be stuck at. And when you do, I will just assert that the thing in the brackets for 3 is going to be a minus 10 over a cubed f of a minus 1/6 f triple prime of a. That's all going to multiply x cubed, and we demand it to be 0, but again, we're looking just at the thing in the brackets. That's our term 3. All right, so our term 3 is equal to minus 10 over a cubed. Our f of a is minus c a to the negative 3 minus 1/6. The third derivative works out to be 60 c a to the negative 6. So, all right, this is a to the negative 6. And, oh, crap, that's 0, too. All right, so that means that it's not going to do for us just to look at the third term. So I will invite you then to go ahead and explore the fourth term. And again, because it's an even numbered term, all we need here for stability is just that be unequal for instability, that be unequal to 0. So anyway, the appropriate thing in the brackets is going to turn out to be, oops, I forgot my mx double dot there, sorry. The thing in the brackets here is just going to turn out to be 15 over a to the 4 f of a minus 1/24 times the fourth derivative of a. I refuse to write quadruple prime. I go to small Roman numerals at that time. X to the 4. We can say mx double dot plus and demand it equals 0. But again, we're just looking at the thing in the brackets 4. So we look at the thing in the brackets. That equals 15 over a to the 4 times minus c a to the negative 3 minus 1/24, and the fourth derivative turns out to be negative 360 c a to the negative 7. Well, a to the negative 3 is going to be divided by a to the 4 is a to the negative 7. Matching c's got a 15 here. And oh hey, when you cancel the 24 into the 360, guess what you get? 15. So it turns out that's 0 as well. So it means we have to go to still yet another higher order derivative. So let's go to the fifth term in the bracket. So all the previous terms drop, so we now are left with an mx double dot plus a negative 21 over a to the 5th f of a minus 1/120th times the fifth derivative of a times x to the 5th, and we demand that be 0. And this whole thing right here is our term number 5. All right, so my term number 5 equals negative 21 over a to the 5th times negative c a to the negative 3 minus 1/120th. The fifth derivative is 2520 times c a to the negative 8. All right, so now let's look at that. Okay, this is a to the negative 8 there. That's a to the negative 8 there. And we're putting 120. Okay, we can drop the zeros. So this gives me 12 into 25 gives me 222. So it's going to be 21 and change. That's 21, but it doesn't matter. They're both negative anyway. So the whole bloody thing is less than 0. Since it's less than 0, that means, and it's an odd term, that means that n equals 3 is also unstable. Whew. So now we can rewrite it as n greater than or equal to, n strictly greater than 3 stable, n less than or equal to 3 unstable. So those are our stable orbits. All right. Now, following this thought a little more here for taking a look at what kind of force laws we may have. Remember, when Newton was working on the idea that gravity was inverse square, Hooke was exploring the possibility that it went just directly as r. So Newton was looking at n to the negative 2. Hooke was looking at n to the 1. Both of them will give closed stable orbits, apparently. Well, that's good. So the book does a treatment on apsidal angles, which I'm not going to repeat here. I think it's a pretty clear one. For our nearly circular orbits. All right, so the apsidal angle is the angle you go through between our min and our max in your orbit. We'll call that psi. In the book's derivation, they show that for the kind of force laws we've been considering, the apsidal angle is equal to the square root of 3 plus n times pi. Now, if we want the orbit to be reentrant, in other words, to close back in on itself, you're going to need psi to be equal to some rational number times pi. So it'll eventually close back in on itself. So let's go take a look just at some integer possibilities. I think you can see that, well, it's not necessarily a mile bad road for non-integer n's, but let's just look at the integer cases. So n equals -2, for instance, which is the world we live in. Our psi would be equal to root 3 minus 2 times pi, or just pi. That's consistent with an ellipse. All right. Let's take a look at some other possibilities. Like say n equals -1. In that case, psi is going to be equal to root 3 minus 1 times pi. Well, that's root 2 pi. So that's not reentrant. It'll never close back in on itself. Let's say the force law went as n equals 0, just for the giggles. Well, then psi would be equal to root 3 minus 0 pi, which is root 3 pi. Again, it wouldn't be reentrant. But if we look at the orbit Hooke was, the force law Hooke was playing with, n equals +1, psi would be equal to root 3 plus 1 pi, which is 2 pi. Well, that's reentrant. What does it look like, though? This is what we call a double ellipse. And I'm not going to draw it well, but I will draw it. It kind of does one of these numbers-ish. It's a double loopy kind of thing. So one of these happens in nature, and one of them doesn't. And so the one that happens in nature is the ellipse, so there you go. All right, now for something kind of different but related, let's go look at scattering. So so far we've been looking at attractive force laws. What if the force law is repulsive? Now scattering is incredibly important. Pretty much all of high energy particle physics is nothing but scattering experiments. There are huge chunks of atomic physics that correspond to scattering experiments. Pretty much all nuclear is scattering. Not all, but a good chunk of it. So it's very important in many fields today. So let's get started with it. So let's start by looking at a hard sphere as our scattering, as our target. We'll just have one of them. So there's our target, hard sphere. Going down the middle there. So let's say we have some object coming in like so. It will come in and then it will scatter off through some angle theta that we call the scattering angle. Now, what angle this is will be dictated by how high in you came in off the center line. So that's a pretty important number. We usually call that B, and its name is the impact parameter. All right. Now, in a typical experiment, you can measure theta, but measuring B, usually not going to happen. Probably where it could theoretically be done the most easily would be in, say, electron energy loss spectroscopy experiments in atomic physics, which I know a thing or two about, from back in the day. And even there, you're talking about impact parameters on the order of maybe 10 to the negative 10, 10 to the negative 11 meters, that kind of range. Just no way that you could set up a beam that fine. So you don't know your impact parameter. But on the other hand, you're also not scattering at just one target. So if we look down at our target assembly, like so. So the beam is coming straight in from above the screen into this assembly. We'll have a whole collection of these hard spheres, which will eventually soften up and turn into atoms. But there we go. And basically we can say either we're going to interact with one of these or we're not. And what counts is as we fly into it, do we wind up hitting this circle here? So this is the cross-sectional area of the thing. Well, if it's a hard sphere, it is anyway. And so we'll say that its cross-section is sigma. So it's measured in square meters or whatever units you prefer. So for a hard sphere, which is what we're considering, the cross-section would be pi times the radius of the sphere squared. Now, typically, the system is, say, a little squishier than that, and the cross-section is really more defining the probability that you're going to significantly interact. All right. So we have a large assembly of these signs. It's going to be too much of a pain to actually count them all even. So we'll let n, lowercase n. Remember, lowercase letters in physics are usually uppercase letters divided by something. So this will be our target density. So this will be the number of scattering centers we have over the area, the total area. So our probability of a hit, of hitting one of the scattering centers, will be equal to the area occupied by the targets over the total area. All right. So the area occupied by the targets will be the number of targets in the assembly. That'll be the target density times the area of the assembly times the cross-section of one target over, we're just dividing by the area of the assembly. Cancel, cancel, we get the target density, the number density times sigma. So our total number of projectiles that are scattered will be equal to the number we fire times the target density times the cross-sectional area. So the target density has units of inverse area. The cross-section has units of area. Okay. So with that, we can start working towards developing, say, Rutherford's experiment. do that, we'll need to define the differential. If we're going to be strictly correct about it, we should say the differential scattering cross-section. No one ever bothers saying the word scattering, though, that I'm aware of. And usually in the literature they just write DCS because that's a mouthful. Okay, so to do this, since to scatter, we could scatter in 3D. We need to come up with the idea of solid angle. So if you remember regular angle, I take a circle and I say that that's my arc length, that's my radius, and the angle in question would be equal to the arc length over the radius. For a solid angle, I would have me a sphere. I'm going to put out some sort of a cone here, or whatever shape. Anyway, it'll occupy some area, and we define the solid angle subtended by this delta omega to be the area subtended over r squared, just following an analogy with the circle. So we can say that one circle has 2 pi radians. Since the surface area of a sphere is 4 pi r squared, we would say that one sphere would occupy 4 pi steradians, S-T-E-R-A-D-I-A-N-S. So just like we write that as rad, we usually write SR for steradian, like so. So a differential of solid angle in spherical coordinates, which are the ones that we're going to use here, d omega would be written as sine theta d theta d phi. Okay, so for our differential, so this gets us into being able to calculate our differential cross-section. So the number scattered into our solid angle element d omega will be equal to the number fired times the target density times the times their cross section. I can chain rule this, d sigma d omega. Hey, I'm good to go. Okay, now I can look at this and say, hey, this d sigma d omega, that is my, this d sigma d omega, that's my differential cross-section DCS. Now, just as an annoying thing, I'm just going to put this off to an aside. In the literature, sigma is often incorrectly called the integrated cross-section, or ICS. And trust me, it's so pervasive that it's not an error anymore. It's just how people say it. And this is because you can get the cross-section, or the ICS, by integrating the differential cross-section. So you're integrating d sigma d omega, which depends on theta and phi, with respect to the solid angle. So this will be integral 0 to pi d theta sine theta integral 0 to 2 pi d phi of our d sigma d omega of theta and phi. And usually you don't have to worry about phi asymmetry usually. So it just becomes a multiplied by 2 pi, at least in atomic physics most of the time. But anyway, the differential cross-section is usually the thing you can experimentally measure. And since you then have to integrate it, people remember going through the pain and anguish of integrating it, so they call it the integrated cross-section when it's really the cross-section. However, it's useful because some experiments do directly measure the cross-section. So this is at least a fast way of you being able to tell, was the cross-section directly measured, or was it calculated from an experiment that measured differential cross sections? So I guess there's that. All right, so now let's go and look at some typical collision. Okay, so here we go. We're coming inbound with some impact parameter B. Yeah, right. Let's try that again. So we're ultimately going to be integrating like so. So as long as I come in anywhere around the axis with impact parameter B, I'll go off to the same place, right? So here's my scattering center. And we'll interact with it somehow and go flying off at some angle theta, right? So if we come in from up here, probably the repulsion is weaker, and so we might come in on the shallower side of that. And if we came in a little closer, you're actually stronger, we'll probably fly out on the little stronger side of that. And so then I am out over here's my new donut, like so. I should say washer, actually. All right, so this bit right here, if I look over here, this is my, I came in with some differential of area, d sigma. That'll be equal to 2 pi times the impact parameter dB. dB. Okay. Now, when I exit here, I am exiting out in some kind of funky differential of solid angle here, and I'm trying to do this in 3D as a volume of revolution, but yeah. So that's what I'm telling you what I'm drawing. So this d omega here, you can work out, that's going to be 2 pi sine theta d theta. Okay. All right, so I can get my differential cross section, whoops, d sigma d omega, literally by just dividing the two. So this will be equal to, absolute values are just fine, 2 pi b dB over 2 pi sine theta d theta. Hey, I can cancel the 2 pi's for what it's worth. Impact parameter is always positive. We can make sine theta positive, so we can write d sigma d omega is equal to b over sine theta dB d theta. Okay, this is cool. D sigma d omega, that's what you're going to measure in an experiment. And the dB d theta, though, that's something that the theoretician can compute. They do go ahead and do their model of thines, and they see how theta and b depend on each other, and then they take the derivative. And the b over sine theta bit, that's just going to be what ties the two together. So now let's look at the example of Rutherford scattering. So in Rutherford's experiment, he had an alpha particle. That's just a helium nucleus, charge Q. impinge on, it was a gold nucleus, so much bigger than a helium nucleus. Charge big Q. All right. So if we follow our same picture here, we're going to come in with some momentum P. We're going to be coming in at some impact parameter B. There's our scattering center there. Long run, we're going to be scattering off at some angle theta, like so, exiting with a momentum P prime after the collision. All right. Now, when Rutherford was playing with this, he remembered his classical physics, because he eventually, what got him really interested, of course, was when he fired the alpha particle at the nucleus, and he saw that some of them basically bounced straight back, which took him totally by surprise. Led him to think that the atom had to have a nucleus, because he was looking at this as just some funky extension of planetary mechanics, which he remembered from his classical mechanics course. All right, I am going to, so the actual path we take, whoops, let's make it a different color. The actual path we take, it's going to be something like this. So again, the standard trick here is we let the bisector this, and this really should have bisected, but again, my crappy art. We'll call that vector U. And we'll just say at any given moment, so let's say at this moment right here, the particle's located right there. This angle here we'll call psi. All right. Now we'll let psi naught equal the limit as t goes to infinity of psi. So that would correspond to that angle right there. All right, so following that thought, we'll get that theta has to equal pi minus 2 psi naught. All right, now if we look at our momenta before and after, if it's elastic scattering, the magnitudes of the momenta will not change. So I just have p prime. It's just a difference in direction. So this would be my angle theta from before. Doggone it. Let's try that again. This bit here would be my delta p, like so. I'll go ahead and throw up a bisector there and observe that the magnitude of my delta p would be 2 times either of these p's, doesn't matter, we're assuming equality of magnitude, times the sine of the half angle. All right, now delta p is parallel to that u vector we constructed. So what that allows me to do is I can calculate my delta p by integrating minus infinity to infinity, just the u component of the force dt. All right, so that will be for Rutherford went ahead and just assumed that the force was the electric force, so he assumed it was like some kqq over r squared. So then this would correspond to integral minus infinity to infinity. Kqq over r squared cosine psi dt. Well, the a little problematic because the psi and the r both depend on t. So we've got to do a little bit of massaging here, but all is not lost. remember that psi dot, by definition, is just deep psi dt. So I could write dt as deep psi over psi dot, if that will help. Oh, but it will, because our reduced angular momentum would be equal to r squared times my psi dot. But we know what that is. It's the angular momentum over m, and that's just going to be the lever arm times the momentum BP. So we can also write it as BP over m. So we can now write my psi dot as BP over mr squared. So that's the angular momentum. That is the moment of inertia of a point mass. So that all makes sense. So now I can write my dt, now this is looking less hanky, as deep psi times mr squared over BP. Okay, so let's go stick that into our integral. So my delta p equals, so this will be integral minus psi naught to psi naught of kqq over r squared, which still depends on t, but hang on, cosine psi, and now we can say deep psi here, and I have to put in my dimensional factor, mr squared over BP. Hallelujah, the r squareds cancel. So I can evaluate the integral. It's going to be kqqm over BP times 2 sine psi naught. But we worked that out from before. We know that 2 psi naught is going to be equal to pi minus theta. And so if you're good with your trig identities, that becomes kqqm over BP times the cosine of the half angle, half the scattering angle. So we have two expressions now for my delta p. One expression for delta p is 2p sine of the half angle. We got that from the vector construction. And the other is this monstrosity we just generated, kqqm over BP cosine of theta over 2. So we can get the impact parameter, because remember what we're all about is differentiating the impact parameter with respect to theta. So the impact parameter we can write as kqqm over p squared, and we get a cosine theta over 2 divided by sine of theta over 2. So that's a cotangent of theta over 2. Now this p squared is m squared v squared. So I'm going to do a quick bit of blackboard math there and just rewrite that as mv squared, like so. So finally, remember we said that d sigma d omega is equal to b over sine theta times d b d theta. Yes. All right, so that's going to be, well, b we can plug in, so we've got here 1 over sine theta. B itself is kq over mv squared. And then I have to differentiate all this with respect to theta. So I'm going to pick up a whole nother kqq over mv squared there. Then I have to differentiate the cotangent. So I'm going to pick up a 1 over 2 sine squared theta over 2 after I differentiate the cotangent and what's inside. Alrighty. Oops, and I forgot that also when oh, sorry, my bad. I jumped way too many steps there. So differentiating the cotangent, we're actually just going to write, I forgot I had the cotangent left from the b, but it'll be more convenient to write it here as cosine theta over 2 down there. Whoops, what am I doing? Sorry, try that again. So mv squared, that's b. I forgot the cotangent of theta over 2. So we'll just leave that as so we have cotangent theta over 2, and then I have to differentiate, so I pick up a whole nother kqq over mv squared, and I have to differentiate that. So I'm going to pick up 1 over 2 sine squared theta over 2, and when we reduce some stuff and the dust all settles, I get d sigma d omega equals kqq over. You can pick up 1/2 mv squared would be the energy. So we wind up getting from the mv squared, so we'll eventually get 4e sine squared of theta over 2 squared. Now, Rutherford saw that his scattering data actually fit that model rather nicely, and so he was able to conclude that yes, indeed, the atom consisted of a very compact, positively charged nucleus, and that the electrons are orbiting at actually some rather large distance compared to the nucleus away from it. Okay, the next series of videos is going to tackle the dynamics of systems of particles.